So I said that in lecture 6 I will explain Bethe approximation, but in this lecture I will cover Bethe entropy, what is Bethe entropy, and also its relation to sum product, a little bit. So these are the fundamental articles, classical articles, if you want to know what is the generalization of belief propagation, because it uses free energy. We have Gibbs free energy, we approximate, we have Bethe free energy, and we want to minimize those things. So recall that this is the probability of the Ising model in physics or in machine learning, some problems in machine learning, in computer vision, for example, or natural language processing, that we can define our probability with simple thing. And our potentials, we can have these indicator functions. And you see that for this term, why do we like this Ising model so much? Because the mu term is just the probability of x equal to j, so it is related to what we want. That is marginal probabilities and probability in general. Even this form as probability, joint probability of x equal to j, and xt equal to k. So it is related to probabilities, these parameters, to the probabilities that we like. So that's why we like this Ising model, because it uses these indicator functions, indicator potentials, and so we can approximate it by. So whenever they write this, it means that theta, a linear combination of theta of your indicator functions, and a linear combination of your indicator functions. So whenever you see this, it means this. Because in the literature, they just write like this. So the shorthand notation for mean parameters are like this that I explained. So the marginal polytope, mu, so at each point is inside here, and these are sufficient statistics at these extreme points, let's say. So there is always a probability that some distribution that which satisfies these things. And that probability should satisfy, so consider a trial set of single node functions and edge-based functions. If these trial marginal distributions are to be globally realizable, they must of course be non-negative. And in addition, each singleton quantity, tau of S, must satisfy this normalization. We can't just pick any distribution. It should be a real distribution. We cannot just take any function. So it should satisfy what a probability does. And so first of all, these are consistency constraints, or people say marginalization constraints, and they should satisfy these constraints. And this local consistency marginal distribution, this M, we want to approximate, in optimization, we either approximate the sets or we approximate the objective. Here we are approximating the set. So we go from mu to L. It's a little off exact things, but it's an approximation that helps a lot. Because now instead of working with mu, we are working with tau. And tau satisfies these conditions that it has a good probability. And you will see in lecture 6 why this is important. I mean, I'm showing this graphically, but in lecture 6 you will see when I work on KL divergence, we want to minimize KL divergence, and we ignore that Z term, and we will see that what is left is Gibbs free energy, and we approximate it by a kind of tree, and we call that Bethe approximation or Bethe free energy, and we minimize the Bethe free energy. And you will see in that term we needed, in that case we needed probability Q, and that probability is now tau. So this is the relation with lecture 6. And the inclusion that M is always inside is a subset of that local polytope that I explained is explained here. And so you know from a previous lecture that this relation holds, and the conjugate dual, we were happy that it's the negative entropy. And now you understand Bethe entropy approximation, because as I said, this relation, we proved it in previous lecture, but this is nothing than minus log of p, expectation of that. And we can write it as entropy minus I, mutual information, which is this one, is mutual information. So the Bethe approximation to the entropy of Markov random field with cycles is described. Although it has cycles, but we have approximated. So this is the entropy for Bethe entropy, let's say. Bethe entropy. Bethe is, Hans Bethe was a great American-German physicist working on nuclear energy, and but now we understand. But some people used it for machine learning as well, and now it is very important for approximation, at least for theoretical purposes. If you don't want to approximate it computationally. So what is the relation between Bethe variational problem and the sum product? So they set this local polytope, locally consistent pseudo-marginal, is convex. And it is an outer bound. You see, this one is outer bound to this one. And the Bethe entropy is an approximation of exact dual function. So by combining these, we understand that the Bethe variational problem. So this is, we want to know what is tau when we make this maximum. And in lecture 6, I expand this and I will show you more clearly using that KL divergence between Q. Q was that approximation. Here we call it tau, and you will see the relation between them. So there are two constraints, as I said, this should satisfy, it should satisfy, this should satisfy. So for that we use Lagrangian multiplier, because this is the term that should be minimized, and these are the terms that should be minimized. So we use these Lagrangian multipliers, or people say dual variables, and this is the Lagrangian of Bethe variation. So we just minimize that. And for that, so why is it related to that? Because what if your Lagrangian multipliers are just the messages? that are passed in that loopy belief propagation, that we don't know what are those things. Now we understand what are those things. And that is the beauty of this Bethe approximation. Because we have shown how mathematically those messages that are very strange for us are related to something that we understand. The Lagrange multipliers, dual variables of this, that in lecture 6 I will show you how those are written in terms of Gibbs free energy or Bethe free energy. So we solve them by putting them the gradient of Lagrangian equal to 0. But what is interesting is that for tree-structured Markov random field, those equations, this one and this one, they have a unique solution. And the optimal value of BVP is equal to the cumulant function. And this is just a proof that we take the partial derivative, set it to 0, you will see these will satisfy. And so this is a long proof. So I explained what is Bethe entropy approximation. So we are generalizing belief propagation. So now, although belief propagation, loopy belief propagation is an approximate method, because when we have a group, when we have a graph with loops, but we will understand how we can, by minimizing the Gibbs free energy in lecture 6, I will show you by minimizing that Gibbs free energy, we can approximate an intractable distribution P, which is hard, by a tractable distribution Q.